Okay, so the next section we're going to talk about is alkynes. So carbon-carbon triple bonds, and there are basically two types that are important. There's a very broad sort of classification for two types. One is what we would call terminal. And so the double bond is on the end of a carbon chain. So this would be an example of a terminal alkyne. The second is what we would call internal. And in this case, you could have the carbon-carbon triple bond is in between. There's carbons on either side. So I've got R here, or R star here, and R here. And so these would all be internal triple bonds. Now, I purposely draw these triple bonds in such a fashion like this. Because why? Because they're linear. So remember, so the carbon on each one of these, all of these carbons in the triple bond here are going to be sp hybrid carbons. So they've each got two p orbitals. So I sort of drawn one here. So this blue orbital is sort of pointing towards us. So there's overlap here. And then the other orbital in the back is sort of dashed. And then we've got the orbital, which is going straight up and down. So this would be sort of in the plane of the blackboard. So the overlap here and overlap here. So overall, these guys are linear. And that's why I draw them in a fashion. So if you do this, this is really not good because they're linear and they've been drawn in a zigzag. So when we're drawing sp2 hybrid carbons, or sorry, sp3 hybrid carbons, drawing it in a zigzag is good because this is helping to depict that these carbons are tetrahedral. But the carbons of alkynes are linear, so they should always be drawn sort of in a linear fashion. That's the best way to do it. So I'll get rid of this one. So they're linear. So that's the first thing. And so if in our little drawing here, I'll draw these. Okay, let's say that this is H. Let's say that this is H. Doesn't matter really. Put our orbitals. We'll draw the other orbitals coming towards us. Okay, let's do a little review here. So that's overlap there, overlap in the background. Let's color this purple. Overlap there, and there's overlap here. Okay, now if I was to ask you, this bond here, I guess I could have drawn this out to the side. What type of orbitals make this bond? What would you say? Carbon uses what? H uses what? So it's a sigma bond because it's a single bond. But what orbitals are being used to make this bond? Okay, so the H orbital is indeed using its S. Hydrogen is using its 1s orbital, right? Because that's what it's got. What type of orbital is the carbon using? Right, an sp hybrid orbital, sp. So the carbon itself is sp hybridized, so it's got the orbitals it has to use are a p orbital, and I'll draw this one sort of so it's coming towards us, and then two sp hybrid orbitals. So here is one of the s orbitals. Well, I'm actually using the other carbon. Here is the other, sorry, here's one p orbital, here's the other p orbital. So one p orbital is over here, one p orbital is here, and the sp orbital. So the two p orbitals are used to make the double bonds, right? Or the two pi bonds to be specific. And that means that this carbon, the hybrid orbitals are the two sigma bonds. So in this interior carbon here, each carbon would be using an sp-sp hybrid orbital to make that sigma bond. So remember, sigma bonds use hybrid orbitals to make them if we're using hybridization theory. So that's what's going on there. So the sigma bonds are sp or are sp hybrid orbitals. This becomes important a bit later on because there's something special about sp hybrid orbitals that we're going to use. Okay. Right. Now, let's talk about some chemistry. Okay. How about how would we make a carbon-carbon? How do we make a carbon-carbon triple bond? So if we needed to make, and if you want to think about this question, just think, how do we make carbon-carbon double bonds? So how do we make carbon-carbon double bonds? What was the main reaction that we learned on how to make carbon-carbon double bonds? Right, we did elimination reactions, and so E2 would be a very good one because that's the most efficient way to do it. So if we had, say this, we could make two different types of, well, technically we could probably make three different types of carbon-carbon double bonds by, we can make this, or we could make this. And we would just use a base, and depending upon the type of base we used, we could make the terminal or the internal, basically double bonds. Do we remember what type of base was good for the Hoffman elimination products, which would be this one? Bulky, right. Okay, so we'd use something like tert-butoxide. And if we wanted to make the other one, we would use like a smaller base. So we could use methoxide, methanol. Okay, good. So we make alkenes from E2 elimination reactions. So it's no surprise to make an alkyne that we just basically do elimination times 2. So what we need is two alkyl halides. We need two halides, and we need twice the equivalency for the amount of base. So there's a couple of examples of, here's a nice little example. So if we were to take this compound here, and we were to do our bromination reaction, Br2 in dichloromethane, we would make the dibromide. And something specific about the dibromide, we'd make the trans dibromide, right? Then what we could do is if we were to treat this with two equivalents of base, so say methoxide in excess, so I'll just put that. What we would end up doing is we would do two elimination reactions. So the first one would be, it would form something like this. And I'm just going to put this in a bracket. And then the second equivalent would eliminate this to form our triple bond. So we would have our H here. It's the elimination is very similar to very similar to, it works very similar. So it goes like this. The main difference is that this elimination is actually taking place on an sp2 hybridized carbon. So that's slightly different than what we've seen. But the key point is that we've made our triple bond. So we've made it from a dihalide. And these two halogens are on, so the bromines are on carbons that are next door to one another. So specifically in this case, a 1,2 dihalide. So this was carbon 1, this would be carbon 2. Now, the halogens don't necessarily have to be on carbons that are next door to one another. You can form alkynes if the two halogens are on the same carbon. So if, for example, if you had this, let's do it like this. Simplify our life here for a second. And we were to use methoxide in excess, then we would make this. So carbon A is here, carbon B is here, carbon A, carbon B. And so the intermediate that we would go through would look like this. On our way to there. So it's like an elimination reaction twice. Now there is, so in this case, and in this case, you still have a dihalide, but they're both on the same carbon. So we would call this a 1,1 dihalide or a 2,2 dihalide. But they're both on the same carbon. So they can be on carbons next door to one another, or they can be on the same carbon. And if you use excess base, you're going to form the alkyne. If you've got a situation like this, and you use excess methoxide, you would form this compound. Once you do the first elimination, it's very rare to make, because there'd be another, you could say to yourself, well, I could take a proton from this carbon, or I could take a proton from this carbon. And if I did that, the product you make is this. So we'll number these carbons 1, 2, and 3. 1, 2, and 3. These compounds here are called alkenes. And typically, they're not formed from these types of reactions. You typically get the typically get the alkyne. You can make alkenes, but this isn't the most effective way of doing it because alkynes are a major side product. So just keep that in mind. For the sake of what we're doing in our class, if we have a 1,1 dihalide and you can remove a proton from either side, just assume that you make the alkyne as the major product. The alkenes, they've got interesting chemistry all by themselves. Yeah, they're kind of cool compounds in many ways, but we might discuss this in a different class, upper level class. So just don't worry about those. So just assume that if we're doing a double elimination, you make the alkyne. So that's basically the ways that we've seen so far of how to make them. So that's kind of new. We know how to make these compounds, these 1,2 dihalides, because we make these from, of course, double bonds and using bromine. So that's very similar. Now, the when we talked about so what we're going to do is we are going to see that, oh no, let me erase this. So some of our favorite reactions from the alkenes, some of our favorite reactions were like addition of HX. We are going to do the same thing. Addition of water. So we had two special reagents for water, the hydroboration or the oxymercuration. We're going to do the same thing. Addition of H2. Same thing. We're going to do the same chemistry. Let's see here. X2. I'm going to do the same thing. It's basically going to be history repeating itself, except for there's going to be some slight nuances in each case. And a lot of the designer reactions that we did at the end with like making the epoxides and the dihydroxylations, none of that, we're not going to really be covering any of the equivalent of that. It's mainly the stuff we did right at the start. And so it's good because it's a nice little review of how things work. So why don't we start with the addition of HX as a polar reaction. So if we were doing HBr, okay, so take a minute or two and think of what the products of these reactions are. Or draw them out, that type of thing. Okay, so if these are alkenes, now, so HBr reaction. So this is the rich get richer Markovnikov addition. So the carbon with the most number of protons is going to get the H. So in this case, in the top case, we would have this as our product, right? This would be the sole product. Because one carbon has got, the carbon in yellow has got more protons, so the rich get richer. Now, the carbon on the second reaction, you'll notice that both carbons, the yellow carbon and the blue carbon, each have one proton each. So we would expect that there would be two products that could form. We could form this, and we would form, so the blue one. So if the blue carbon gets the proton, we would make this. So we would have two products. Now, I think I said before, organic chemists, when you're doing a reaction, there's a whole bunch of things that you want to have happen. One of the things you want the reaction to take place in high yield. That's good. The second thing is you want to limit your side reactions. So of these two reactions, one of them produces one product, the other one produces two products. So the bottom reaction isn't as useful, right? Because you've got a mixture of two things. So this reaction here isn't useful. Because separating these two things is going to be a pain. So if you wanted to make the product in blue, you would notice that these two guys are the same, right? Ones I've underlined. So it'd be better to have the double bond on the end and do it in that fashion. Okay, now why am I talking about this? You will notice that in each of these cases, in one case, the double bonds on the end of a carbon chain, and the other case, the double bonds in the middle of a carbon chain. So by extension, if we do the same reaction of an alkyne, HBr, put excess here. In the case of a terminal alkyne, the first step would be the rich get richer. One carbon here has got a proton. The other carbon has none. So we would expect that this would get, oops, the proton. Actually, we can draw it in yellow, it doesn't matter. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this would be the product after the first step. And the final product, which we'll draw over here, the rich still get richer. So this carbon on the end, carbon 5, 4, 5, still has more protons. So our product is going to be look at that, a 1,1 dibromide. So they're both on the same carbon. That's why it's called 1,1. Now, if we do, so after the first step, it's going down the same, you start in going down the corridor and you keep on going down that same corridor. For an internal alkyne, we're going to see that we're going to run into problems if we try this same reaction, right? So with an internal one, and I'm going to give you the heads up at the start, this reaction isn't very useful. Unless the molecule is somehow symmetrical. This one isn't. I'm drawing one which isn't so symmetrical. So you'll notice that each of these carbons has got the same number of protons, which is 0. So we would expect each carbon, so step 1, HBr. After step 1, we're going to form 2 products. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. H. So we'll call this one carbon A. We'll call this one carbon B. So this is carbon A, B, A, B. you'll notice that we should get a statistical mixture of the two, right? But then once you've made that the first step, then in the second step, now one carbon does have more protons than the other carbon, so the rich can get richer. So this will solely form again, a dibromide. And this one here will form, again, a dibromide. So this one's on carbon B, A, B. But again, this would be a mixture of the two, so that's why it's not particularly useful. So when we're adding, so the moral of the story, it's taken 20 minutes, but the moral of the story here is that if you're doing an addition of HBr to an alkyne, it's a particularly useful reaction with terminal alkynes. So that's basically where I was going. With internal ones, unless the molecule is symmetrical, it's not particularly useful. What's an example of something which is symmetrical? So what do I mean by that? So if our compound was this, so ethyl groups on either side, the first step would be and this is the same as these two molecules are the same. They're just drawn from a different perspective. So if you basically stick a nail right here in this molecule, and then you rotate it in this direction. So this little middle bit stays in the same place. This bromine's going to come all the way around and end up here, and this proton's going to come all the way down and end up there. So it's the same molecule. And then in the second step, the rich will still get richer, and both of these are going to produce the same thing, which is the two bromines being on the same carbon. So you'll have ethyl on one side and the propyl on the other. So unless the molecule is symmetrical, it's not a particularly useful reaction. But in the cases that it are, it works. But so when we're adding HBr to a alkyne, terminal alkynes work the best. So that's the addition of HBr. The addition of, like, say, Br2, all we're doing here, and the reaction really doesn't matter if it's internal or external, but if you've got, say, chloromethane, what we're going to end up doing is brominating each carbon twice. So we would have, we've got 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5. And we're brominating carbons 4 and 5 twice. So we'll have BR, ER, BR. And the last thing on this little carbon here, of course, is the proton. And if we had an internal double bond, one, two, three, four, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So carbons 4 and 5 have got bromines, Br, Br. Erase this mess. PR. I don't know why I'm compelled to draw these lone pairs. It's just a weird compulsion. I never used to. Something's happened to me in old age. Okay, so we'd have a tetrabromide in each one of these cases. So somebody at some stage found these molecules interesting, so you can make them. So it's basically the bromination just happens twice. There's nothing particularly interesting about it. Yes, and I guess it's true. If we were to be really, really careful, yeah, I guess I should bring this up. If you were being really, really careful, so let's say that we had this, and we used exactly one equivalent of Br2. Our final product is going to look like this. So the two bromines should be on the opposite sides of the carbons. So they should be basically, so if we were to assign a configuration to this double bond, what would the configuration be? Is it E or is it Z? Whole bunch of people saying E. That's correct. So the highest priority in each case, carbon versus bromine. Okay, bromine's the highest priority. Bromine's the highest priority. And so when they're opposite to one another, that is E. Z means same. E means opposite, I think. It was the German words. These are E. You'd make an E alkyne if you used specifically one equivalent of bromine. So that's actually, that is kind of interesting. So and it's very similar. You'd have that sort of bromonium ion, and the bromine would attack from the opposite side, except for there's a double bond there. So you'd have something which resembles this. And you would need to have the Br minus come in. On the opposite side. It looks ugly. Yeah, it does look a bit ugly, but that's what everyone says it is. So anyway, the important part is that if you ever were to do this, the two bromines should be on opposite sides. Okay. All right, so we've got like 5 minutes left. So the two really interesting reactions coming up are the addition of water and the addition of H2. So we will probably do the addition of water first. So just to remind everybody, so when we were adding water to an alkene, there were two conditions, BH3 and THF, followed by H2O2 and hydroxide. So in this case, if you if you had a double bond, the OH group would be on the opposite side. It would be on the least substituted carbon. And the other key important thing is that these two groups would be on the same side. And then the OH on least substituted carbon. So anti-Markovnikov. The second one that we did was the oxymercuration. So Hg, OAC, 2 water, and THF. Then sodium borohydride. Now, when it comes to alkynes, so if we have the same molecule here, and we did use these conditions, we would end up with, after the first step, we would have OH, Hg, OAC, and then the second step would be reduced. So that's how that worked. Now, just before we get on, like next, we'll start the next class. When it comes to the reaction conditions for alkynes, the sodium borohydride one is exactly the same, completely the same. The only difference that we're going to see in the oxymercuration thing is that they use a different reagent, HgSO4, and they don't actually need the sodium borohydride for the second step. It's just done in a mixture of mainly water with some, pardon me, some sulfuric acid. So we'll see, we'll talk about this at the start of next class. Pardon me, at the start of next class. So there's just a slight change in the mercury reagent, but what we're going to see is that, again, these two reactions are going to be completely complementary. One's going to do one thing, the other one's going to do the opposite. So that'll be good. And then the reaction with hydrogen, we're going to be able to make cis double bonds and trans double bonds and that sort of fun stuff. So that will be useful as well. So, and then basically after that, we've essentially finished all of the alkyne chemistry. I'll just remind everybody before we go about SN2 reactions. Think back to what made a good nucleophile. So what made a good nucleophile? And think back to the acidity of protons on different carbons. So sp3 versus sp2 versus sp. Just think about that before next class, because we're going to talk about, besides those two other things, this guy, because that's important. All right, now I'm sorry I'm late. There was a chat question here. Yeah, so I'm gonna, there's been two questions about the midterm, which we'll talk about on Tuesday, because it's not until the following week. And there's another question about having an assignment. So I'll put up an assignment for this weekend to give you some practice. And then we'll talk about the midterm on Tuesday and Thursday, I guess. All right. Okay, yeah, sorry I went over time a little bit, but yeah, it won't take long to finish off the rest of this sort of thing, because it's basically the same chemistry. It's just happening twice in a row. That's basically the point. And some of the stuff isn't actually useful and some of it is. So I'll try to limit it to the things that are useful. All right. So have a good day, everybody. I hope the lab went well yesterday, and we'll see everybody shortly. Okay, now I will end this.